Welcome back to the deep dive. About 6 months ago, there was this prevailing narrative in the Valley, and frankly, in my own head, that the architecture we are going to be talking about today was effectively dead on arrival.
Oh, completely.
Right. Because we were looking at the release of Gemini 1.5 Pro, we were looking at GPT-4's massively expanding context windows. And the thought was just, why bother?
Yeah, why build a system when you can just paste everything into the prompt?
Exactly. Why build a complex retrieval system when I can just place an entire library into the prompt and hit enter? And for you listening, today we are diving deep into a stack of engineering reports, primarily anchored by some staggering new adoption metrics from Databricks, to explore exactly why that brute force approach didn't win out. Our mission today is to take you on a complete tour through the engine room of modern AI. We are unpacking REA.
Retrieval-Augmented Generation, and it really is the engine room right now.
It is. The Databricks report we have on the desk this morning paints a completely different picture than the one we had 6 months ago. We are looking at over 60% of large language model applications in enterprises now leveraging RAG. It's not dying, it's becoming the standard operating system.
And I'd argue that 60% figure is actually conservative, especially if you look at successful production-grade deployments. The Databricks data is so fascinating because they are actually seeing the back-end compute cycles. They aren't just sending out a survey.
Right, they see the real usage.
Exactly. And what they were seeing is that the huge context window, it's great for reading a novel or maybe analyzing a specific self-contained legal contract, but it is frankly terrible for a living, breathing corporate archive.
Because of the needle in a haystack problem.
That and the sheer economics of it. There is a massive difference between what we call parametric and non-parametric memory. And misunderstanding that difference is exactly why so many CFOs are having absolute heart attacks when they see their API bills right now.
Okay, let's pause there, because that distinction, parametric versus non-parametric,
Yeah.
that is effectively the thesis statement for this entire deep dive. So let's break that down for the listener. Parametric is the model's brain, right? The actual weights.
Correct. Think of parametric memory like your own long-term memory. It's deep, it's highly intuitive, it understands syntax, logic, how to speak French, how to write Python, but it's fuzzy. And crucially, it is frozen in time.
Frozen, meaning once the training stops, it stops learning.
Right. Once you train a massive model, it's baked. It does not know the stock price of a company today. It doesn't know what the CEO said on an earnings call yesterday, unless you retrain it, which
Costs millions of dollars.
billions of dollars and takes months of compute.
And that's where the hallucinations come in, isn't it? Because the model inherently wants to be helpful. It has been fine-tuned to be an obedient, helpful assistant. So if you ask it a question it doesn't know the answer to, it just improvises based on patterns it learned 2 years ago.
Exactly. The analogy I always use is, imagine asking a brilliant, world-class historian who has been in a coma since 2021 to analyze today's geopolitical landscape.
Wow. Yeah, they'd sound incredibly smart.
Very articulate, but the actual facts would be completely fabricated, and that's where RAG comes in. RAG is the non-parametric memory.
The external storage.
Right. It's the open book on the desk during an exam. It is entirely dynamic. You can swap out a single page in that book without performing multi-million-dollar brain surgery on the model itself.
That is a phenomenal way to frame it, the open book exam. And the source data bears this out in a huge way. We're seeing from the reports that RAG-based responses are nearly 43% more accurate than those from LLMs relying solely on fine-tuning.
43%, that is massive.
It's not a marginal gain at all. That is literally the difference between a cool tech demo and a secure tool you can actually deploy to a Fortune 500 client.
It's the difference between trust and a massive liability.
It's so true. And that's why today is going to be a highly technical deep dive. We are going to tear apart this architecture piece by piece. We'll look at the specific flavors of RAG, from agentic to graph, and we're going to decode these buzzwords you keep hearing in meetings like high DE and vector embeddings. Let's get right into the mechanics. Segment 1, how this actually works.
Let's do.
Because RAG isn't just a single thing you turn on, right? It's a pipeline. It's a chain of highly dependent operations. And if one link breaks, the whole system just collapses. The very first link is data ingestion.
Which I know sounds like the most boring part of the process. But ask any data engineer working in the trenches right now, and they will tell you this is exactly where the war is won or lost.
Because enterprise data isn't sitting in nice, clean text files.
Oh, far from it. It is an absolute mess. You have data trapped in PDFs. You have messy 50-deep email chains. You have SQL databases. You have Slack logs with memes and emojis and weird threading.
Hmm.
The very first step of RAGI is just building the plumbing to connect to all these diverse sources and extract the raw text.
And PDFs are the arch nemesis here, aren't they? The documentation makes it sound like parsing PDFs is the bane of every AI developer's existence.
It is a total nightmare. Think about a standard corporate financial report. You've got columns. You've got data tables spanning multiple pages, headers, footers, tiny margin notes. If you just run a standard naive text extractor over that document, it reads linearly across the page.
Meaning it reads across the columns instead of down them.
Yes, so it grabs line 1 of column A, then line 1 of column B, then line 2 of column A. It literally turns coherent financial data into absolute gibberish.
So when the AI model eventually gets it, it just sees a random jumble of words and numbers.
Precisely, and it can't reason over that. So you need highly sophisticated optical character recognition, or OCR, and layout analysis tools. The sources point to things like unstructured or llama parse. These tools don't just read the text. They figure out what order the words are actually supposed to be in based on the visual layout.
Because if you mess up that ingestion phase, the rest of the pipeline is pointless.
Garbage in, garbage out. The vector database can't fix a broken sentence.
Okay, so let's assume we've run the gauntlet. We have successfully scraped and cleaned the text. We have massive clean strings of enterprise data. Now we hit the concept of chunking. And looking at the research, this seems to be the part of the stack where there is the most intense debate right now.
Yes, the art of chunking. And it truly is an art form. The naive thing to do, which is what practically everyone does when they build their first weekend prototype, is to just chop the text up blindly every, say, 500 words and shove those chunks into the database.
Why is that a problem, though? I mean, 500 words is a solid paragraph or two. That seems like a decent size to feed an LLM.
It's completely arbitrary. Human language doesn't work in fixed 500-word blocks. If you cut a document blindly by a character count, you are incredibly likely to slice a crucial sentence right in half. Or worse, you might separate the context from the fact.
Give me an example of what that looks like in practice.
Okay, imagine an HR document. The text says, "The company policy on remote work is incredibly strict and generally prohibited." And then the very next sentence, which happens to fall into the next chunk, says, "However, exceptions are always made for the engineering and product teams."
Oh, I see.
Right. So if a user asks about remote work, the system might only retrieve that first chunk because it matches the keywords. The LLM then confidently tells the user, remote work is strictly prohibited. It completely misses the nuance because the chunking strategy severed the relationship between those two sentences.
You lose the semantic integrity of the document.
You do, which is why the industry has moved to what's called recursive character splitting. You don't just chop blindly. You look for natural structural breaks. You try to split by paragraphs first. If a paragraph is still too large for the model, then you look for punctuation to split by sentences. If the sentence is massive, only then do you break it by words. You are actively trying to keep logical ideas grouped together.
And the sources also mention the concept of overlap here.
Yeah, overlap is a great safety net. You might have a chunk of 500 tokens, but you intentionally overlap it by 50 or 100 tokens with the subsequent chunk.
Like a sliding window over the text.
Exactly like a sliding window. This ensures that if a core concept does happen to span across your cut line, at least one of those chunks is going to contain the full, unfragmented context.
But even recursive splitting feels a bit mechanical. The deeper research dives into things like semantic chunking and parent-child indexing. These seem to be where the serious enterprise teams are landing.
Yes, parent-child, which is sometimes called small-to-big retrieval, is an incredibly powerful architectural pattern. Here is the underlying logic. When you're searching a database, small chunks are actually better.
Because they're highly specific.
Right, they're dense with specific meaning. They match a user's specific query very closely. But when it comes time to actually generate an answer, small chunks are terrible because they lack the surrounding context.
Right, the LLM needs the broader picture to sound intelligent. So parent-child solves this by completely decoupling the search from the generation.
You nailed it. You chop your source document into tiny child chunks, maybe just a single sentence or two.
Yeah.
You index those tiny sentences for the search algorithm, but in the database, each child is permanently linked to a larger parent chunk, maybe the entire page or the full section it came from.
So when the user asks a question, the system searches the child chunks.
Then finds the exact sentence with the exact fact. But it doesn't send that tiny sentence to the LLM. It grabs the parent chunk that the child belongs to and sends that whole page to the model.
That is just so clever. You get the absolute precision of searching for a needle, but you deliver the whole haystack to the LLM so it understands the context of the needle.
Exactly. It significantly reduces what we call the lost in the middle phenomenon, where the LLM misinterprets a fact because it has no idea what preceded or followed it.
Okay, so we've expertly chunked our data. Now we get to the part of the deep dive that frankly always sounds the most sci-fi to me, embedding. We are taking this text and turning it into numbers. And not just basic numbers, we're talking about high-dimensional vectors.
High-dimensional floating point numbers. This is the core translation layer of modern AI. Computers at a fundamental level do not understand the word king or queen or apple. They only understand math. So we use a specialized embedding model, something like OpenAI's Text Embedding 3, or the models from Cohere, to map these text chunks into a massive multidimensional mathematical space.
The documentation always uses the analogy of a 3D map because human brains just can't visualize anything larger. But we're usually talking about massive dimensionality here, aren't we?
Oh, absolutely massive. The older BERT models from a few years ago were 768 dimensions. The newer enterprise models are 1,536 dimensions, or even over 3,000 dimensions.
Over 3,000 axes on a graph.
Imagine a graph with 3,000 different directions. Every single concept, every nuance in human language is assigned a highly specific set of coordinates in that hyperspace.
And the absolute magic of this, the reason the RAG works at all, is that the embedding model places semantically similar concepts physically near each other in that space.
That's the secret sauce. The words lawyer and attorney will be located at almost the exact same coordinates in that 3,000 dimensional space, even though they share absolutely no letters in common.
Because they mean the same thing.
Right. The word apple, the fruit, will be clustered in one area of the graph, right next to pie and orchard and pear, but Apple, the tech company, will be placed in a completely different galaxy of the graph, clustered near Microsoft and stock market and iPhone.
But there's a massive catch here that the reports highlight, and I think people often overlook it when they first get into this. Embeddings are essentially a form of lossy compression. You are taking a complex paragraph full of nuance, tone, and specific details, and you are squashing it down into a fixed list of numbers. You inherently lose some detail.
That is a crucial point for anyone building these systems. This is exactly why pure dense retrieval, which means using only vectors, sometimes fails spectacularly on a very specific niche queries.
Give me an example of a dense retrieval failure.
Okay, say you work in manufacturing. You search your internal database for a very specific part number, like screw-type-404. The embedding model, because it compresses meaning, might just map that query to the general conceptual neighborhood of hardware or fasteners.
So instead of retrieving the manual for that specific screw, it retrieves a generic manual about how to use a screwdriver.
Exactly, because in the vector space, screw 404 and screw 405 are practically sitting on top of each other. They are mathematically too close to distinguish purely by meaning. They mean the same thing conceptually. This is why you can't just abandon exact keyword matching, which we'll get into when we discuss hybrid search.
Right. So moving down the pipeline, we have these massive vectors. We store them in a vector database. The sources mention platforms like Pinecone, Weaviate, Milvus, Chroma. This database is effectively where the company's knowledge lives.
It's the new library.
So when I, the user, ask a question in the chat interface, the system takes my question, converts it into its own vector, and does a nearest neighbor search.
It calculates the mathematical distance. Usually it's using formulas like cosine similarity or dot product. It's fundamentally asking the database which data chunks have the most similar trajectory and angle to this user's question vector.
And it pulls up, say, the top 20 most similar chunks. But we aren't done yet, are we? Because as we established, just being mathematically similar doesn't mean it's actually the right answer to the specific question.
No, it doesn't. Vector search is incredibly fast, but it's an approximation. It's fuzzy. And that is exactly why the modern enterprise stack almost universally includes a re-ranker.
The quality control step.
Exactly. Think of the vector database as a highly energetic, very fast junior intern. You ask a question, and the intern sprints to the library and brings back 20 books that vaguely match the topic. They might be relevant, they might not.
They just grabbed whatever was in the right section.
Right. The re-ranker, on the other hand, is the senior tenured professor. The professor takes those 20 books from the intern, sits down, reads the specific pages, and says, no, this one is completely irrelevant. This one contradicts the premise. But this one document, number 5, this contains the exact precise answer.
And technologically, the re-ranker is what's called a cross-encoder, right?
Yes. This gets a bit into the weeds, but it's important. The initial vector search uses biencoders, which means it processes the user query and the database documents completely separately. That's why I can search millions of records in milliseconds. But the re-ranker uses a cross-encoder, which processes the user's query and the retrieved document together simultaneously.
It looks at the relationship between the two.
Exactly. It's deeply analyzing how the query and the text interact. It's much slower, it's computationally much heavier, but it is infinitely more accurate. It rescores that list of 20 and maybe only passes the absolute best top 3 documents to the LLM.
So you are intentionally trading a tiny bit of latency, maybe an extra half second of wait time, for a massive, massive jump in precision.
And in an enterprise setting where accuracy is everything, that trade is almost always worth it. If you send bad or irrelevant context to the LLM, you are practically begging for hallucinations. The re-ranker is your firewall against bad context.
Which brings us to the final step of the pipeline, generation. We take those top 3 meticulously selected chunks, we glue them into the prompt, and we essentially tell the LLM, answer the user's question, but only use the information provided right here. And that gives us grounded generation.
That's the holy grail of this entire architecture. The model stops improvising, it stops making things up, and it starts doing what it does best, synthesizing and summarizing text.
So that is the core pipeline. It is highly logical, but as we've just discussed, it is prone to failure at practically every single step if you aren't careful. And looking at the broader evolution outlined in our sources, RAG has had to evolve incredibly rapidly to patch these specific holes. The reports break this evolution into 3 distinct paradigms: naive RAG, advanced RAG, and modular RAG. Let's trace that history. Naive RAG, I assume this is basically what we just described, but stripped of all the safety rails.
Yeah, naive RAG is the V1 approach. It's a straight line. Retrieve, then generate. No re-ranking, no complex chunking, no query rewriting.
And the failure mode there is pretty obvious.
It's just garbage in, garbage out. If a user asks a vague or poorly worded question, the retrieval mechanism fails. If the retrieval brings back loosely related but factually irrelevant documents, the LLM hallucinates based on that bad data. It works fine if you're building a simple weekend project or a basic FAQ bot, but the minute you try to use it for complex reasoning, it falls apart.
Which pushed the industry toward advanced RAG. And based on the Databricks numbers, this seems to be where most sophisticated enterprise teams are operating today.
Advanced RAG is all about adding targeted logic and optimization to the pipeline. It introduces what we call pre-retrieval and post-retrieval strategies. So pre-retrieval might be something like query rewriting.
Which is necessary because, frankly, human users are terrible at asking questions.
They are the worst. A user will literally open an HR chatbot and just type the word salary.
Just one word?
It's just one word. And a pure vector search for the word salary is going to return half the database. It's too broad. But a query rewriter acts as a middleman. It takes salary, looks at the user's profile, and rewrites the prompt in the background to say, what are the salary bands for senior engineering roles in the Seattle office for 2024?
It turns a lazy query into a highly optimized search vector.
Exactly. And then your post-retrieval strategies include things like the re-ranking we just talked about. It's all about ensuring that the context window is high signal and low noise.
And then there is the third paradigm, modular RAG. This sounds very much like the microservices approach in traditional software engineering.
That is the absolute best analogy for it. In modular RAG, the system is no longer a monolithic pipeline. It is composed of highly swappable, independent modules. You have a distinct retriever module, a generator module, a filter, a rewriter.
Why is that so important right now?
Because of the sheer velocity of the AI field, we are getting a new state-of-the-art embedding model or a new re-ranker practically every Tuesday. If you build a monolith, you have to tear the whole thing down to upgrade. With modular RAG, if Cohere releases a better re-ranker tomorrow, you just swap that specific module out. It's plug and play.
And it also allows for dynamic routing, doesn't it?
Yes. You might have a system where if the query is about legal compliance, it routes through a very specific dense retriever fine-tuned on law. But if the query is asking for a specific part number, it routes to a sparse keyword search module. It's highly adaptable.
Okay, speaking of routing traffic, let's get into the main event here, the menu. Segment 3, The sources identify several highly specific flavors of R that have emerged to solve different enterprise problems. This is where the architecture really starts to fracture into specialized use cases. We organize these into three functional buckets. First up, Group A, which we are calling the intelligent researchers.
This is where the most cutting-edge, frankly, mind-blowing work is happening right now, and leading that pack is Agentic REG.
Agentic. It is undeniably the buzzword of the year. Every pitch deck has the word agent in it. But what does Agentic ARG actually look like in the server logs? How is it fundamentally different from a standard advanced ARG search?
It looks less like a search and more like a stream of consciousness. In standard RAG, the process is linear. The user asks, the system searches, the system answers, one shot, pass or fail. Agentic ARG is a loop. The system actually has agency. It has the ability to plan and execute tools.
Give me a concrete scenario. Walk me through a query that would instantly break a normal RGAG system but succeeds with an agent.
Okay, let's say you are a financial analyst. You type this prompt into your terminal. How has the CEO's tone regarding artificial intelligence investment changed between the Q1 2022 earnings call and the Q3 2023 earnings call?
Yeah, that is a nightmare query because there is no single document in existence that contains that answer. A vector search for that entire sentence would probably just return a random earnings call that happens to mention AI.
Right. It would fail completely. An agentic system, however, pauses. It looks at the prompt and essentially says to itself, I cannot answer this with one search. I need a multi-step plan.
It breaks it down.
It creates a to-do list. Step 1. Use the search tool to retrieve the Q1 2022 transcript. Step 2. Retrieve the Q3 2023 transcript. Step 3. Extract only the sections where the CEO is the active speaker. Step 4. Filter those extractions for the terms AI or artificial intelligence. Step 5. Perform a sentiment analysis on both sets of quotes. Step 6. Compare them and write a summary.
It's literally orchestrating a multi-step research project.
It is. But here's the truly agentic part. What happens when it tries to execute step 1 and fails? Let's say the file in the database isn't actually named Q1 2022.
A normal script would just throw a 404 error and stop.
Exactly. The agent actually reasons through the failure. It looks at the error and says, okay, document not found, alternative action, let me search the database for first quarter 2022 instead. Or let me use the list directory tool to see all files from 2022 and manually select the one from March. It self-corrects on the fly. It loops and loops until it satisfies its own goal.
That is a massive paradigm shift.
Yeah.
You are essentially replacing the junior analyst who does the data gathering, not just the search bar. But I have to assume there's a massive compute cost associated with this.
Huge cost and significant latency. That single query we just talked about might take 45 seconds or a minute to run. It might burn 10,000 tokens iterating through failures. You absolutely do not use Agentic RAG for a customer asking, how do I reset my password?
Right, that's overkill.
Use it for high-value complex synthesis where the depth of the answer justifies the compute cost.
Okay, next in this intelligent researcher group is GraphR. This has been getting an incredible amount of attention, especially since Microsoft Research published their big paper on it. This is all about knowledge graphs.
Yes, standard WARG deals with text matching. GraphR deals with relationships. It utilizes a knowledge graph database, something like Neo4j. Think of a knowledge graph not as a spreadsheet, but as a giant spider web connecting entities.
So it maps the connections between things.
Right. The node for Elon Musk is connected by a line to the node for Tesla, which is connected to electric vehicles, which is connected to lithium batteries.
But why do we need a separate graph for that? Can't the LLM just figure out those relationships by reading the raw text in a standard RAG setup?
Not always, and certainly not efficiently. Imagine a complex investigative journalism scenario or a legal discovery process. You have a dump of thousands of leaked corporate emails. You want to know, how is person A connected to person B? The actual text of the emails might never mention person A and person B in the same document.
So a vector search would never link them?
Never, because their documents aren't semantically similar. But person A emailed person C, and person C emailed person B.
The transitive property of corporate corruption.
Exactly. A vector search misses it entirely. But a graph traversal algorithm finds that hidden path instantly because the relationships are mathematically explicitly defined in the database. Microsoft's research highlighted that for global questions that require understanding the holistic dataset rather than just finding one isolated fact, GraphRA is vastly superior.
And what about the efficiency? Building the graph sounds expensive.
Building it up front is expensive, yes. You have to use an LLM to extract all those entities and relationships from your raw text. But once the graph is built, querying it is surprisingly efficient. The Microsoft paper found it requires anywhere from 26 to 97% fewer tokens than other multi-hop approaches to answer those broad summary questions.
It's because you are feeding the LLM a highly compressed map of relationships, not hundreds of pages of raw email text.
Precisely. It's incredibly elegant.
All right, the third architecture in the intelligent researcher bucket is HIDE, spelled H-2-A-D-E, hypothetical document embedding. Honestly, when I first read about this one in the sources, it sounded like a psychological trick being played on the machine.
It is absolutely a reverse psychology hack, and it exists to solve a very specific, very human problem, a vocabulary mismatch. Users often ask terrible questions, or they use completely different terminology than the experts who wrote the documentation.
Right, like a patient asking a medical portal, why does my tummy hurt? When all the clinical documents in the database talk about abdominal distension or gastroenteritis.
Exactly. Tummy hurt and abdominal distension might not be physically close enough in the vector space if the embedding model isn't perfectly tuned for medical slang, so a standard search fails. Heidi solves this by asking the LLM to intentionally hallucinate first.
Wait, I thought the entire point of this architecture was to stop hallucinations.
Stick with me here. The system intercepts the user's question, why does my tummy hurt? And it sends a hidden prompt to the LLM. It says, write a hypothetical, highly technical medical diagnosis for a patient presenting with tummy pain. The LLM generates a paragraph. Now, that paragraph might be completely factually wrong about the user's actual disease.
But it will use the right words.
Yes, it will use the words gastritis, appendicitis, abdominal cavity. It generates the expert-level terminology. Then the system takes that fake hypothetical answer, vectorizes it, and searches the database with that vector.
Oh, wow. So you aren't searching for the user's simplistic question at all. You are searching for the expert documents that mathematically resemble the AI's hypothetical expert answer.
That is exactly it. You use the LLM's vast parametric memory to bridge the semantic gap between the layman user and the highly technical database. It works incredibly well in fields like medicine, law, and engineering, where that terminology gap is the primary barrier to search.
That is genuinely brilliant. Okay, let's pivot to Group B, the self-correctors. These architectures are heavily focused on rigorous quality control. The main two highlighted in the deep dive sources are self-RAG and corrective RAG, or CRAG.
These are geared towards solving the ultimate enterprise hurdle, which is trust. Self-RAG is essentially about giving the model the ability to introspect. It generates an answer, but simultaneously it generates what researchers call reflection tokens. It is literally grading its own work in real time.
Like a student taking a test, but pausing after every sentence to check their own logic against the textbook.
Yes, it generates a sentence and then evaluates. Is the sentence relevant to the prompt? Yes or no. Is the sentence directly supported by the retrieved text? Yes or no. If it generates a no token, it halts, deletes the sentence, and attempts to generate a new one.
So it is proactively filtering its own hallucinations before the user ever sees them.
It maximizes the probability of a purely factual response. And CRAG Corrective RAG takes this philosophy a step further. It focuses heavily on evaluating the retrieval step itself. If the vector search comes back and the evaluator model looks at the documents and says, these have really low relevant scores, CRAG doesn't just shrug and try to force an answer anyway.
Because it knows it has bad ingredients.
Right. It triggers a corrective action. It might try to strip away the irrelevant paragraphs from the documents to salvage something. Or, crucially, it might trigger an external web search. It basically says, my internal corporate database failed me. I am going to securely query Google or Bing to augment this before I answer.
It fundamentally refuses to settle for, I don't know, or worse, a confident lie. That seems absolutely critical for use cases like policy analysis or compliance, where accuracy is non-negotiable.
Absolutely. It's about engineering a structural safety net into the workflow.
All right, moving to Group C, speed and context. This is all about the user experience. The sources highlight conversational RAG, speculative RAG, and adaptive RAG.
Conversational RAG is pretty much the baseline expectation now. It adds short-term memory to the system. If I ask a bot, who is the CEO of Microsoft? And it answers, and then my next prompt is just, how old is he? The system needs to maintain the state. It needs to know he refers to Satya Nadella.
Right, it stores the chat history in a buffer.
Exactly. And practically what it does is it silently rewrites your second question to how old is Satya Nadella before it hits the vector database. Because if you just search a vector database for the word he, it's going to fail completely. Without conversational memory, interacting with these bots feels like talking to someone with severe amnesia.
What about speculative RAG? The name alone sounds aggressive.
It's highly predictive. It analyzes the flow of the current conversation and attempts to guess what you were going to ask next. If we are deep into a chat about a specific new laptop model and I just ask about the processor speed, the system thinks historically users who ask about the processor next ask about the battery life or the price.
And it preemptively fetches those documents in the background.
Yes. While you are reading the answer about the processor, it is already running the RVIG pipeline for battery life. So when you inevitably do ask about the battery, the answer is rendered instantly. It artificially reduces the perceived latency to 0. It's a clever UX trick.
And finally in this group, adaptive RAG, which the literature refers to as the traffic controller.
This is purely a cost and latency optimization play. Not every single question requires a complex $10 multi-step agentic RAG workflow. If a user logs in and just says, "Hi," or "What is the support email?" you absolutely do not need to spin up a reasoning agent to read the whole database. Adaptive RAG classifies the complexity of the query up front.
It triages the request before processing it.
Exactly. Is it a simple greeting? Route it to a tiny, incredibly fast, cheap model with no retrieval. Is it a complex synthesis question? Route it to the heavy agentic loop. Is it ambiguous? Route it to a clarifying agent that asks the user what they mean. It dynamically balances the compute cost against the required quality.
We have covered so much ground on the mechanics and the menu. Now I want to shift gears and ensure our listeners are armed with the right vocabulary to actually navigate these architecture meetings. Segment 4 is the tech stack and glossary. We touched briefly on search techniques earlier, but let's clearly define the battle between dense, sparse, and hybrid retrieval.
This is the fundamental debate in search architecture right now. Sparse retrieval is the old school, tried and true method. Think of algorithms like BM25. It strictly matches keywords. If you type in the word kidney, it looks through the database for the exact character string KIDNEY.
It's effectively Streetrill plus F on steroids.
It is, and people dismiss it as legacy tech, but it is actually incredibly hard to beat for highly specific queries. If you are a mechanic searching a manual for a specific error code, like error 505, sparse keyword matching is perfect. It will find exactly that. Dense retrieval, on the other hand, uses the vector embeddings we talked about. It matches meaning, not letters. Kidney and renal are mathematically close.
But, as we discussed with the screw example earlier, dense can drift and fail on exact matches.
It can. It generalizes too much sometimes, and that is exactly why hybrid search has emerged as the definitive gold standard. You literally run both systems simultaneously. You get a list of results from the BM25 keyword search, and you get a separate list from the vector similarity search. Then you use a mathematical algorithm, usually something called reciprocal rank fusion, or RRF, to merge and re-rank those two lists into one final master list.
So you are basically covering all your bases. If I search a medical database for renal failure treatment protocol 505, the dense vector search pulls in documents conceptually related to renal treatment, and the sparse keyword search locks onto the exact number 505, and the fusion algorithm guarantees the final document contains both the concept and the specific identifier.
Precisely. It makes the system incredibly robust to different types of user questions.
Next up in the glossary, evaluation. How do we objectively measure if a newly built RA system actually works, or if it's just generating confident garbage? The literature heavily references something called the RA triad.
The RAG triad is the industry standard framework for evaluation. It breaks success down into 3 distinct measurable metrics. First, context relevance. Did the retrieval mechanism actually find the right stuff in the database? Is the retrieved text useful? Second, groundedness. Did the LLM stick strictly to the facts provided in that context, or did it start freestyling and hallucinating its own facts? And third, answer relevance. Did the final generated response actually answer the specific question the user asked?
That third one is tricky, because you could have a perfectly grounded answer. For example, the model outputs, "The sky is blue," based on the provided text, which is factually true, but completely irrelevant if my original question was about corporate tax law.
Exactly. An answer can be grounded but useless. You need a high score on all 3 pillars of the triad to pass. And the great news for developers is that there are now open source frameworks, the most popular being RAGAS, spelled RAGAS, that automate these exact metrics. You can run 10,000 synthetic test questions through your pipeline overnight and get a definitive quantitative score on how well your architecture is performing.
I want to tackle one massive point of confusion before we move to the future outlook. It comes up constantly. Fine-tuning versus RAG. I still hear smart people in the industry say, why go through all this trouble to build a complex R pipeline? Why don't we just fine-tune a model directly on all our company data?
Oh, this is easily the most common misconception I run into. It fundamentally misunderstands what fine-tuning is for. Fine-tuning is primarily for teaching a model a new behavior, a style, or a specific skill. If you want your AI to speak entirely in the style of Shakespeare, or if you need it to output code in a very weird proprietary programming language or format-specific JSON payloads, you fine-tune it. You're adjusting the fundamental weights to change how it acts.
But you shouldn't use it to teach the model new facts.
It is a terrible, highly inefficient way to teach facts. It brings us right back to the parametric memory problem we started with. Trying to bake a company's entire factual database into a model's weights is incredibly expensive, it's agonizingly slow, and the literal second you finish the training run, those facts are outdated. Plus, even if you fine-tune it on your documents, the model can and will still hallucinate details. RAG is for providing dynamic, verifiable knowledge. Fine-tuning is for modifying behavior.
So the ideal state-of-the-art enterprise stack might actually be a combination. A model that is fine-tuned to perfectly understand complex medical jargon, the skill-connected VRA to a constantly updating database of patient records the knowledge.
That is the ultimate winning combination right now. They are entirely complementary technologies, not mutually exclusive options.
Okay, segment 5, the future outlook. Where is all of this going? The deep dive sources highlight a few specific emerging trends that are poised to reshape this architecture. The first is multimodal RAG.
This is huge. Up until very recently when we said RO, we implicitly meant text. We were searching text to generate text. But the real enterprise world is fundamentally multimodal. It's full of images, complex charts, audio recordings, and video files. Multimodal RO allows us to embed and retrieve across all these different media types simultaneously.
So I could conceptually search a massive corporate video archive.
Yes. By leveraging vision models like OpenAI's CLAP, you can generate vector embeddings for specific frames of a video. You could type a prompt saying, find me the exact moment in last month's all-hands Zoom meeting where the VP of Sales showed the Q4 budget projection chart. And the system could search the visual content, find that specific slide, extract the audio transcript from that moment, and generate a text summary of the strategy discussed.
That unlocks an unfathomable amount of dark data that is currently just trapped in recorded calls and unsearchable slide decks.
It's going to be revolutionary for institutional knowledge. Another massive trend gaining traction is federated ERG. This is entirely focused on solving the privacy and compliance bottleneck. In highly regulated sectors like healthcare, defense, or finance, you often physically cannot move all your data into a single centralized cloud database to build an ERG system. It violates data residency laws.
So how does federated ARG bypass that restriction?
Instead of moving the sensitive data to the central model, you bring the model to the data. The AI orchestrator operates across decentralized, disparate data sources. When a doctor asks a question, the system might simultaneously send a query to Hospital A's local secure server for patient history and a separate query to a research university server for clinical trial data. It retrieves the answers locally and combines the insights without the raw, sensitive data ever leaving its original secure environment.
Wow. And finally, the sources mention RLRAG, reinforcement learning applied to retrieval.
This is the concept of a system that actively gets smarter the more it is deployed. It relies heavily on user feedback loops. If a user asks a question, gets an answer, and clicks a thumbs up icon, the system logs that. It learns, the specific retrieval strategy and writing path I used for that query was successful. If they click thumbs down, it adjusts its internal weights. Over time, the system autonomously optimizes its own retrieval policies based on real-world human preference.
It organically evolves to serve the user better.
Exactly.
We have covered an immense amount of ground today, from the fundamental mechanics of recursive chunking and high-dimensional embedding all the way up to the sophisticated multi-step architectures of Agentic and GraphAge. As we wrap up this deep dive, I want to try to summarize the massive paradigm shift we are witnessing here. Looking at the data, it really feels like the entire industry is moving away from the assumption that the model needs to know everything.
That is the ultimate takeaway. For a long time, the arms race was purely about building bigger and bigger parametric models. Let's just train it on the entire internet and hope it memorizes everything. But enterprise developers quickly realized that is not enough. It's too static. The shift right now is heavily towards the philosophy that the architecture needs to know how to find everything. OR-RAID fundamentally transforms the LLM from a static, arrogant know-it-all into a highly skilled, meticulous researcher armed with a library card.
It builds a sturdy bridge between the frozen, abstract intelligence of the neural network and the messy, dynamic, real-time factual needs of the real world. It turns the notorious black box of AI into an auditable system that we can actually inspect, verify, and trust in production.
Precisely. It brings accountability to the generation.
Which leaves us with a final, slightly provocative thought for you, the listener, to mull over as we sign off. As we see the continuous rise of these ultra-long context LLMs models that can swallow entire books or massive code bases in a single prompt, does RA eventually become obsolete if compute gets cheap enough that I can just paste the entire corporate library into the prompt every single time? Do I even need a complex retrieval architecture anymore?
That is the billion-dollar question in the Valley right now.
Yeah.
Some people do view RA as merely a temporary bridge technology, but I think the consensus among engineers actually deploying these systems is moving firmly towards a hybrid future. Even if you mathematically can fit a massive book into the prompt, it is inherently inefficient, expensive, and slower. And what if you don't have one book? What if you have 10,000 books? You will never fit the whole world into the context window. The future is almost certainly a combination. Utilizing massive context windows for incredibly deep reasoning and synthesis, combined with highly targeted, highly intelligent retrieval systems like GraphRAG to find the exact right needles in the infinite haystack. It's not about bigger models replacing retrieval, it's about smarter retrieval unlocking the true potential of bigger models.
The future isn't just big, it's organized. Thank you for joining us on this deep dive into the architecture of truth. We will see you in the next one.
Thanks for listening.